All right, let's go over how you pull in data for a multi-season occupancy model. So we've got program mark pulled up. We'll just go File, New, and we're going to come down to Robust Design Occupancy. And you'll see you'll have a whole bunch of different alternatives that you can select here. The first is occupancy estimation with psi and epsilon. So you would have psi changing each time, and epsilon, your extinction parameter, estimation with psi gamma. Okay, but the one that is generally used is this third one, which is psi 1 gamma epsilon. And basically with this, you're saying I'm going to first estimate occupancy for that first time period. And then from that point on, I want to see how changes in immigration, gamma, and extinction, epsilon, influence psi for each subsequent year or time period. And generally, if you're starting with some uh, basic standard situation, maybe you're applying treatments, you want to see what the effects are, that would be appropriate. A situation where you might do this is, say you were monitoring spotted owl populations, and you wanted to see how occupancy changed as a function of clear cuts being put in a particular area that you're monitoring. And so you have information on clear cut acreage that's put in each year, and you're thinking that's going to be best to explain epsilon. You're interested in modeling psi. I don't know. Anyway, that's again for you to decide. These other ones, you can have heterogeneity estimation, random effects, and then false positives and so on. Okay, so we've got the model that we want. Let's select our file, and that's going to be the Blue Ridge salamanders. And um, there's something interesting that they did with the input data on this. And if I can move this over, I will show you. So if you read in the Mark book, you'll see that they did three surveys in the first year. And then for subsequent years, they decided to up it to 5 surveys. So you'll notice that there's 2 dots following the first 3 entries. And basically, they just did that to sort of make it simpler when you read in the data. So now we can say that each year has 5 surveys. There's 4 years, so that's 20 surveys. Another way you could do it is say there's actually 18 surveys. The first year there's 3, and all the rest there are 5. However you want to do it. And you can see that we have 2 groups. One, first are group 1 are sites that are near streams. These are salamanders, so you might expect that they like to be near streams. That's where the adults spend, that's where they go and breed. And then group 2 is far from streams, okay? And then we have another individual covariate. So this applies to all the different sites, and we've got 39 sites, and we have the elevation of that site. So we would need to indicate that there's 20 occasions, 2 attribute groups, 1 individual covariate. We can use the easy robust design because of the way that we entered the data. And what that'll do is it'll assume that there's 5 observations or surveys each year. We click OK. Another thing to look at are the time intervals, and you'll see that there will be 4 zeros and then a 1, the 1 indicating that we have a year in between the next surveys, and then 4 zeros and a 1, 4 zeros and a 1, and then 4 zeros. Okay. Oh, I've got 19 here, not 20. Um, yeah, because those are intervals. Sorry. Um, and two attribute groups, so we need to put those in. So near, uh, stream, and far stream. Okay. And then one covariate, which is elevation. So we're all good to go now. We can click OK and OK. And if we look at our PIM for this completely parameterized model, so you see that we have a initial occupancy psi for near stream and far from stream. Those are our two groups. And then we have, and of course that's it. We just estimate psi that first time and then look at extinction and immigration for all the rest of the time intervals. And psi then will be a derived parameter. And so now we can have extinction for each of those intervals near the stream, extinction for each interval far, immigration near, immigration far, and then your detection probabilities for each of the occasions in the first year, near, first year far, second year near, second year far, and so on all the way up. So lots of parameters here. We have 54, in fact, and I've already put this in so I didn't have to type it up. So I'm just going to kind of simplify things here. It's psi in parentheses G, indicating the two groups near and far from stream. Epsilon is just abbreviated E, G times T, gamma, G times T, and P, G times T. Okay, so I'll just go ahead and run that. Okay, and then what they suggest, and this is, again, depending on your species and situation and so on, you would might assume that your capture probabilities or detection probabilities are constant within a year for the two different sites. So you just click on this first string of P's and say constant. So what we're going to do is just make a model that sets those P's to be constant. We're going to allow them to differ between years and differ between near versus far from the stream, because you might expect that detection probabilities would differ near to far. Okay, and then we can just do a renumber. Doesn't matter in this case, no overlap. So now what we're going to run is psi g um, epsilon gt gamma gt, and then psi session g. Okay, so we're going to allow it to vary by session and by group. Okay, so I'll run this, and psi g is right, e gt g gt, and then I'm going to type in here just so I know what's going on. Pi or p session times group. Okay, so that'll kind of simplify things for us, and we can start with that when we do our design matrix. Okay, so following the approach they use in the book, then they go with the simplest model where you're setting your everything to be constant. So we'll do this with a design and reduced, and initially we're going to keep it very simple. We'll just go with 4 columns. Okay, and in this case we just have we'll have a 1 for the two psis. Okay, we're going to force those two to be the same, the initial occupancy. Here's epsilon, going to do the same thing. There's 6 values there because there's 3 intervals and 2 groups. Okay, same thing for gamma. 6 ones, and then for P, you're just going to have, again, whoops, not 11, a series of ones. So this is our dot model, okay? So we could run that. We could also run this using the PIM. And so this would be psi dot E dot G dot and P dot, okay? So we'll click OK to run, yes. And boom, it pops in there. Now, let's say we want to do something maybe a little more interesting or realistic. Say we want to look at psi, gamma, and epsilon and see if they vary by group, by whether you're near or far from the stream. So we're going to have to add some columns. I'll just click on this second column and then I'll say insert one column, and then to add the group effect for psi, I just put a 1 in that second column. Okay, here's the intercept now. The second column would be the effect of being near versus far from the stream. We can do the same thing for the epsilon, but now we're going to have our constant for epsilon, all 6, and then the last 3 epsilon values in that next column will all be 1s, okay? And finally insert one more column and we do basically the same thing for gamma. Okay, so just, take a look at that, make sure you see what's going on. We've got a constant or intercept and a group effect for psi, epsilon, and gamma. So we can run that. And in this case, we would have psi. I'll call it stream, and epsilon stream, and gamma stream, and finally P stream. Okay, and we should be okay to run, and we say yeah, and just want to, yeah, okay. And now we want to add some more complexity. Maybe say you think that because there's been a drought over time that these parameters might basically be declining sort of monotonically over time. So if we start with this, so what we're going to assume now is that we start with just one occupancy for both the near stream and far stream. Obviously, you could decide maybe you want to do that differently, but just to follow them. So I'm just going to delete this one column. Okay, so now psi just has the single column. It's going to force them both to be equal. And now for epsilon and gamma, I'm going to put a linear values 1, 2, 3 in this third column. So again, constant for epsilon, and then for the near stream, you have epsilon declining or increasing, whatever it is, by a constant amount each time step. Same thing for the far from stream, and we do that for the gamma values as well. And so these are going to be additive terms. And so this would just be G or epsilon big T, gamma big T. We have basically intercept and a slope. So if we run this, we're going to have, and this is a good way to do it, put in the year so you know that you're coming up with a constant estimate for psi in that first year, and then a time effect for gamma, and oh, did I think I put a p stream. It should have been a p dot. Okay. All right. So this looks like what we want. So we can say OK to run, and it'll stick it in there. And then the final one is basically adding the elevation to the stream model. And let me check this. Yeah, this model, I have that named wrong. That should be P, change model name. That's not P stream, that's P dot. Okay, can go in and change that if you realize you did it wrong. Now we'll pull that one up, and we want to do basically the same thing we did when we built this. We want to add a column in here, and then we want to put in elevation. Okay, and we do that for both of the psi values. Okay, then we do the same over here for epsilon. Going to insert a column, and in this case we are going to put individual covariates into all 6 of those cells. So what I'm going to do is click on that, right click, and say copy value down, and I want to copy it 6 times. Okay, hit it, and then boom, we've got elevation for all of our epsilons. We still got our near versus far distinction, and then finally add 1 column, and we want to do basically the same thing. Put in our individual covariate, and then do it for all 6. And that should work out. Okay, so we go and we run that, and that will refer to as our stream plus elevation model for all of these parameters. It's plus because we didn't put in the interaction term. And G plus elevation, and then P. Okay, we click OK to run. And one thing you'll notice, I ran another model here that they didn't in the book, and that was that one where you had constant P times G model that we used to get our design matrix. But if you look at, so in the book, the top model will be the psi stream, epsilon stream, gamma stream, P dot. Okay, but you'll notice that for theirs, the AIC is 690, and we have it as 688. And the reason is that Mark estimated it to be only 6 parameters, whereas it's 7. So if I open this quickly, you see there's 7 columns, so it should be estimating 7 parameters. And why didn't it do that? Well, if you look at the real parameters, and I'll drag it over here, you see that the initial psi for the sites near the stream was 1. Basically, all of them were occupied, and so it's not estimating that, or it's assuming that that's not an actual parameter because it's got 0 standard error. And so what we would need to do then is to change the parameter number to 7 so that it matches what it actually should. And I believe we have the same problem for the next one. So we estimate that as 9 parameters. And if we retrieve it, it should actually have 10. Okay, so we want to change that one to 10 parameters. And I don't know if when they ran it in the book, it for some reason didn't mess up. This should be 4, and that's right. Let's see if that makes sense. Yep, 6. So I think we're okay for these others. Although this one I think we also underestimate, but we could have some time confounded variables. I'm not going to worry about that one. So let's look at what would have been the top model in the book and take a look at the estimates associated with it. And first off, you can see that psi for the near stream sites is higher than psi for the far stream heights, basically 100% versus 92%. And then we had epsilon being constant between years for the near streams, okay, about 9% extinction. Look what's happening here. Far from streams, you get about 50% extinction, so a lot more of those sites are blinking out. Gamma 0.74 for immigration into sites that had formerly not been occupied, and immigration on the far sites is much lower. So basically, because you're getting a lot more extinction than immigration on those far sites, the occupancy is going to be declining. Then, of course, we set P to be equal for all of those sessions. And then the final thing I'll show you are the the derived estimates. So for those, we just click on the little blue square, and this obviously would be something to be interested in because this is telling you the estimated proportion of occupied sites for those sites near the stream. Okay, so notice we got psi hat here, so it goes from 1 to 91% to 89%. Okay, to stays about the same at 89% in year 4. Okay, so now we have 4 estimates because we get an estimate of psi at each occasion. And then you see for those sites farther away from the stream, starts pretty high, 92, then drops very quickly to 46, 32, 28. Okay. Another piece of information it gives you, which can be very helpful or useful from a management perspective, is lambda hat. So lambda is the growth rate of, in population modeling, it's n sub t plus 1 divided by n sub t. So if it's greater than 1, the population's going up. If it's less than 1, it's going down. And notice here, it's pretty self-evident. So for the near stream sites, the first year everything was occupied, and then it was at 0.98. Okay, so that makes sense that lambda would be 0.908 because it would be 0.908 divided by 1. Okay, so then for the next lambda, it would be 0.838938 divided by zero point 0.9. Okay, and that's also going to be less than 1, but much closer to 1, indicating that it's declining, but not very fast between year 2 and 3. And then basically between year 3 and 4, pretty much stays the same. So your lambda is very close to 1. But notice now for the far sites, you have basically a 50% decline in the number of sites that are occupied. So your lambda is 0.5, and then you do continue to get declines, but not as rapidly as that first year. Okay. And then finally, they give you this other parameter called lambda prime, which is the ratio of the odds ratios. So the odds ratio you calculate for each year by taking the proportion of sites that are occupied and dividing that by 1 minus the proportion of sites that are occupied. So if we look at these last 2 years for the sites away from the stream, you see for year 3 you have 0.3254. Okay, so the odds ratio in that case would be 0.3254 divided by 1 minus 0.3254, and that would give you an odds ratio of about 0.48249 or something, meaning that it's basically what are the odds of a site being occupied. Okay, so it's about 0.32 divided by 0.68, so that means that you know most of the sites are unoccupied, and the probability that a site is occupied relative to being unoccupied is about 50%. Okay, and you see that drops a little bit on the next year, so that odds ratio would be 0.2819 divided by minus 1.2819, and that gives you an odds ratio of about 0.39. Okay, and what this value is would be the ratio of those odds ratios. And to me, I don't know, I just find it gets a little hard to get your head all around that. I guess in certain situations that might be useful. To give you like a simpler numbers to go with, say you had occupancy of 0.75 in 2000 and 0.5 in 2001. The odds ratio in 2000 would be 0.75 divided by 0.25, or 3 to 1. They're 3 times more likely that a site will be occupied than unoccupied. And in 2001, it would be 0.5 divided by 0.5, or 1. It's basically, there's an equal chance of a site being occupied versus unoccupied. So if you looked at the ratio of those two, it would be 1 divided by 3, or 0.33. And basically that tells you that the odds ratio has dropped by threefold between those 2 years. Or if you look at it backwards and say go from 2001 to 2000, in that case there would be a 3 times greater chance that a site would be occupied versus not in 2000 versus 2001. Anyway, it's just, again, another way to look at how these things are changing. I tend to like to look at Lambda because that just is a lot more intuitive to me. All right. I think that's got it all. Hope that helps. Bye-bye.